In this lesson, we're going to take an examination of some of the more common applications of dot products and cross products. We'll talk about dot products first. One of the most common applications is the idea of work. We started looking at this when we looked at vector projections. And work happens when you move an object. You can move it forward, you can move it up, you can move it down, move it in diagonal. We usually measure in joules or in newtons per meters. The amount of work that's actually being done depends on two things: the direction that you're applying your force and how far you're actually moving something. That's called our displacement. If we go back to the beginning of this unit, when we first started talking about forces, and we had our wagon, and we had a wagon full of books and we wanted to move it, we talked about vector projections, and we talked about, well, we want to pull on that handle, but the amount of work that's actually being done is in the direction of the way the wagon's moving. Okay? So we have to talk about our components of force. I'm hoping you would agree from this diagram that we can take the wagon idea and break the resultant, the force that we're actually using, into two parts, the horizontal and the vertical part. If we actually move the wagon in the direction horizontally that we want it to go, so if we move it this way, the amount of work that's being done is how much horizontal force is happening, how much force is happening here, times how far I actually move it. And the further I move something, the more work I have to do, and that should make sense. Okay, so we have a little formula for work. Okay, it's your component of force, that would be your horizontal in this case, because you want to move your wagon horizontally, times how far you need to move something, so the displacement of the object. Okay, so a simple application, a simple example of it. Here, look at the wagon again. We have a child pulling a wagon with a constant force of 30 newtons. So if we draw our wagon in, here's our wagon, little wheels, and he's pulling with 30 newtons of force. How much work is actually done in moving the wagon 100 meters if the handle makes an angle of 30 with the ground? So we want to move the wagon this way and keep dragging until we've gone a total of 100 meters. That would be our displacement. So I'm going to write that down here on the side here, my displacement equals 100 meters. So if I want to know how much work, I need two parts. I need the force in the direction I want to move something times our displacement. We just figured our displacement was 100. So the only thing I'm really missing is what force is going in that direction. So the force in that direction would be the horizontal force. If we turn this into a right triangle, it told us we're making an angle of 30 with the ground. The force I want, it would be this horizontal force right there. To calculate that, I can use SOHCAHTOA. In particular, the horizontal force would be my adjacent. The 30 newtons the child's pulling with is your hypotenuse, so we can use cos. So the cos of 30 equals our horizontal force over the 30 newtons. So that's 30. If we cross multiply that, we get FH equals 30 cos 30. And if we put that into our calculator, we end up with 26 newtons. That's how much force is actually moving the wagon in the horizontal direction. So combining that with our displacement, for every meter we move, we need 26 newtons. We're actually using 2,600 joules of force. Okay. Try a second one. I've got a 400 kilogram crate sitting at the bottom of a 10-meter long inclined ramp. So we have a ramp. Okay, it's sitting down here at the bottom. Actually, put the bottom right here. And we're trying to push that thing up the ramp. Our ramp is 10 meters long. It makes an angle of 30 with the ground. So we can put 30 in here. How much work is required to slide the crate to the top, assuming no friction? So, first things first, the crate. The crate isn't being measured in terms of a force being applied. It's being measured in terms of weight. Well, we deal with forces. We deal with vectors. Weight, mass, 400 kilograms, isn't a vector. So we got to turn into a vector first. And so let's start here. Mass into, I gotta turn a mass into a weight. That's the first thing we have to do. Because a weight has a direction attached to it. Direction is downwards. It's based on gravity. Okay. So the force of gravity, a number we will come across over and over again, is 9.8 newtons downwards. That's per kilogram. So if I have 400 kilograms and 9.8 is my force of gravity, that comes out to 3,920 newtons. That's holding that crate at the bottom of the ramp. It's making it go downwards. 3,920 newtons. So if I want to know how much work I need to just slide the crate up the ramp, I want to slide the crate this way. My work, we saw previously, is F times S. I need to figure out how much force I need to counteract the gravity. How much force do I need to get it up the ramp? And then I'm going to multiply that by how far I have to move it up the ramp, so times 10. So how do I figure out that force going up the ramp? Well, again, it's right angled. This is my opposite, my hypotenuse this time, so I can use sine. So the sine of 30 equals my opposite, 3920, over the hypotenuse, the force that I want. I need to push this force up the ramp. Cross multiply that, F sine 30 equals 3920, and then divide out the sine 30 part. And divide out the sine 30 part. And for a force, we'll get 7,840 newtons. That's how much force I would need to counteract the effect of gravity that's holding the crate down. How much work do I have to do? My work is going to be my force, 7840, times the displacement, 10 meters. So I need to use 78,400 joules of force. And that's some sort of simple applications, the idea of force. And those really are dot product ideas, even though we're not using the dot product. We're using the idea of multiplying two vectors together. A common application of the cross product is the calculation of areas, in particular parallelograms and triangles. Okay. The area of a parallelogram created by two vectors that are meeting tail by tail can always be found by the cross product of those two vectors, and then take its magnitude. Because remember, vector, cross product produces a vector which has components, and we can find its magnitude. If I want to do a triangle is just a special version of the parallelogram. If you stop and think, my parallelogram will go like this, and my triangle is half of that. So I can do the magnitude of a cross product divided by 2, and I can find the area of a triangle fairly quickly. And this works in 3D, obviously, 3 dimensions. So for example, I want to find the area of the parallelogram defined by A and B. First thing I want to do is find my cross product. So we're going to write down A cross B. I'm just going to write them underneath each other, so I'll do the fast way. And we'll do the cover-up method. So cover up the x's, we'll get 4 minus 6. We'll get negative 4 minus 0 on the opposite sign. And we'll get negative 3 minus 0. So we end up with negative 2, negative 4, but the opposite sign, and negative 3. Okay, and there's your components of the cross product. If I want to find the actual area, area equals the magnitude of that cross product. So it'll be the square root of negative 2 squared, 4 squared, plus negative 3 squared. You put it all in, and you end up with root 29 units. And we just have units because three-dimensional, we don't know what's being measured in. And until we find a parallelogram, we can do the same thing for a triangle, except for remember our area formula would be A cross B divided by 2. Okay, so I've got 3 points that are forming my triangle. Points aren't really helpful to us. We want to turn these into vectors. So I need to figure out one vector. I'll call it A. Maybe that's going to be my AB idea. So if I subtract, I get -1, 0, -1. If I try a second one, we'll call that AC. It wouldn't matter if I did BC, that's totally fine also. And I'll get 0 and -1 and -2. And I want to do the cross product of those two things. So if I say A cross B, because they're written on top of each other, makes that idea the quick one to do. We'll get 0 minus 1. We'll get 2 minus 0, but the opposite sign. And we'll get 1 minus 0. So -1, -2, and 1. So our area is the magnitude. -1 squared plus -2 squared plus 1 squared all divided by 2, which is root 6 over 2. You can leave it like that for an exact answer. Okay, and there's some simple applications of dot products and cross products. In particular, the two formulas you want to know are the ones that go with the parallelogram and the triangle.